Hello, everyone. In this lesson, we will continue our discussion on the application of input relay I and output relay Q instructions. As illustrated, the input button SB1 corresponds to system storage I0.0, with the state of SB1 determining the status of I0.0. Let's delve into the specifics. Input relays, also known as input image registers, serve to receive input signals from field devices such as control buttons, limit switches, and various sensors. As shown, these relays are physically connected to external buttons, limit switches, and sensors. The status of an input relay is updated during the input sampling phase of each scan cycle, receiving input signals 1 or 0 from the field. Input relays come in two types: normally open (NO) and normally closed (NC) contacts. The latter diagram for NO and NC contacts of the input relays is depicted in the figure. The address for these relays is a bit address. There is no limit to the number of times you can use NO and NC contacts of input relays. These contacts can be freely used within the PLC. Since the input image registers of the S7-1200 series PLC are byte-oriented, the CPU typically reads a relay's status using bit addressing. It can also read the status of adjacent groups of relays by byte, IB, 8 bits, word, IW, 2 bytes, 16 bits, or double word, ID, 4 bytes, 32 bits. The provided figure shows an application example of input relays. From the figure, we can see that the input relay I instruction is primarily used for input signals, not for output signals. Input relays can be connected in series or in parallel with other signals, Q0.2. Next, we will explain the output relay Q instruction. As illustrated, output relays correspond one-to-one with external interfaces. When the Q instruction is high, the external interface outputs a signal. When the Q instruction is low, the external interface does not output a signal. From the analysis above, it is evident that output relays are designed to drive external load components, with actual physical contacts connecting them to the external load. They consist of coils, NO contacts, and NC contacts. The coil controls the contact's actions. When the coil is activated, the NO contact and NC contact will act accordingly. When the coil is energized, the NO contacts close and the NC contacts open. Conversely, when the coil is de-energized, NO contacts open and NC contacts close. There is no limit to the number of times NO and NC contacts of output relays can be used, and their operation is driven by the coil. Energizing the output relay coil has two implications. First, it causes the NO and NC contacts to actuate. NO contacts close and NC contacts open. Second, it connects the output signal port to the corresponding common point. The output relay is also addressed in a byte.bit format to read the status of a relay. Additionally, it can read the status of adjacent relays by byte, QB, 8 bits, word, QW, 2 bytes or 16 bits, or double word, QD, 4 bytes or 32 bits. The figure provided shows an example of output relay applications. When I0.4 and I0.3 are de-energized, Q0.3, Q0.4, and Q0.5 are all non-conductive. When I0.4 is energized and I0.3 is de-energized, Q0.5 conducts while Q0.3 and Q0.4 do not. When both I0.4 and I0.3 are energized, Q0.3 and Q0.4 conduct, and Q0.5 also conducts. This illustrates that output relays are used for PLC output signals and are typically located at the network's end. Output relays can be connected in parallel or series as needed. Now, let's proceed with practical demonstrations of the learned content through application cases. Case 1. Start, stop, and continuous operation circuit control of motors. This case involves controlling a single motor's start, stop, and continuous operations. Pressing the start button initiates the motor, and it continues running after releasing the start button. Pressing the stop button halts the motor immediately. This includes both power-on priority and power-off priority circuits. The power-off priority circuit means that regardless of the start button's state, pressing the stop button will cut off the output. The power-on priority circuit means that regardless of the stop button's state, pressing the start button will energize the output coil. Task implementation. 1. I/O address assignment. For start, stop, and continuous operation control of a motor, a button is required to start the motor and another to stop it. Additionally, a thermal relay is added for safety protection. Therefore, there are 3 input signals, as shown in the table. Since only one motor is controlled, the input count is 1. 2. I/O wiring diagram. Since both input and output signals are DC 24 volts, connections are made as illustrated. Connect the start, stop, and thermal relay to I0.0, I0.1, and I0.2, respectively, and the motor control relay Ka is connected to Q0.0. The diagram shows the programming for a power-off priority of start, stop, and continuous operation circuit. Here, I0.0 is the start button, which is a no button because pressing it energizes the motor. I0.1 is the stop button, NC button because pressing it cuts off the motor. To ensure continuous motor operation, a latching control is added. For power-off priority, the stop button is placed on the network's main line to ensure that both the start button line and the latching line can be disconnected. The diagram also shows the power-on priority program. Similar to the power-off priority program, I0.0 is the start button and I0.1 is the stop button. To ensure power-on priority, pressing the start button will guarantee that the motor receives power. The stop button is placed in the self-latching circuit to ensure that even if the start button is pressed and the stop button is pressed simultaneously, the motor will still be powered on, reflecting the requirement for power-on priority. After downloading the program to the PLC, simulate the program using the simulation software. Set the start button to 1 to check the program's start operation. After successful startup, set the stop button to 1 to check the stop operation. For the power-off priority program, test both start and stop buttons to verify the motor's de-energization. For the power-on priority case, test both buttons to verify the power-on priority. In this lesson, we have learned the ladder diagram formats and applications of NO contacts, NC contacts, coils, and inverted coils instructions. We have understood the states of NO and NC contacts with operands 0 and 1. We also learned that a program cannot have 2 identical coils. Additionally, we clarified the format and meaning of input and output relay instructions. We applied NO, NC, and coil instructions to implement a PLC-controlled motor start, stop, and continuous operation circuit and developed both power-on and power-off priority control programs, laying a foundation for further learning and instruction applications. That concludes this lesson. Thank you, everyone.